Hi, welcome to the second probabilistic programming session. Today we'll be looking at message passing on factor graphs. If you have not done so already, I strongly encourage you to have a look at the lectures on factor graphs, continuous data, and discrete data. So suppose you will finish this course and do an amazing graduation project, and then you find yourself sitting across from an interviewer for a job. That interviewer wants to determine your skill level, but that's not as easy as it sounds. So today we'll be looking at a series of questions that the interviewer can ask you to determine your skill level. And in this first part, we are looking at right or wrong questions. So just questions you can get right or wrong. So think of this as true, false statements, multiple choice, or any other question you can get right or wrong. So we start with an outcome variable, x1, that can be 1 for right, 0 for wrong. And we have a prior on that, a beta distribution theta. The higher theta gets, the more likely are you to get the question right. And so in general also, the larger theta is, the more skill you are perceived to have. So this resembles the model from the first probabilistic programming session, the beer tasting experiment, and we are explicitly having another look at this in the context of factor graphs. So you're going to start with something that's already familiar. So the general model consists of the following. I have a joint distribution p of x1 comma theta that factorizes into p of x1 given theta times p of theta, where p of x1 given theta is a Bernoulli likelihood and p of theta, the prior, is a beta distribution. The company has set the prior parameters alpha and beta to 1, which is going to produce an uninformative prior distribution, and a bit later on I'll give you a clear picture of what that means, an uninformative prior distribution. If we translate this model into a factor graph, we're going to get the following. We have two square nodes, fa and fb. Fa corresponds to the beta prior, and fb corresponds to the Bernoulli likelihood. Theta is the unknown variable, that's the edge connecting those two factors, and we have a measured response, x1, that's the observation of whether you got the first question right or wrong. So we mark observed variables with a black box like this one. If we translate this factor graph into code, we'll do that here. So the reason Fornilab is called Fornilab is because the following is a Forni style factor graph. And so what you do in Fornilab is you start a factor graph and then you start building that graph structure. So we are going to add a prior, or we're going to add a random variable. So add rv is a macro. A macro is a collection of commands summarized into a neat package for readability. So in this case it's random variable, so we're going to add the random variable theta, which is distributed according to a beta distribution. And so this is going to represent the first node. We're going to add another random variable x1, which is distributed according to a Bernoulli distribution whose rate parameter is this theta. So the fact that theta occurs here means that these two nodes are connected. And we can ask Fornilab to draw the graph, which is going to produce something that resembles the clean, neat, hand-drawn graph, except with a bit more detail and annotation. So the observed variable x1 is on the top here. Then we have this f of b likelihood node, the edge connecting f of b to f of a, the prior node, that's this one with theta there. And then Fornilab also reports clamped variables, so clamped parameters. In this case we clamp the prior parameters of this beta to certain values. Now we want Fornilab to generate a message passing procedure for us. So first of all, we need to define which variables we want posteriors for. We do that by this function posterior factorization. This is currently, it does something which is currently not important, so we're not going to go into detail on this. We only have one unknown variable here, so there isn't anything to factorize for this posterior. So we want a message passing algorithm of the unknown variable theta, and then with this Q, this posterior factorization, we can say something about this, the structure of the unknowns, but we only have one unknown. These two lines of code compile the algorithm and bring this into scope so we can use it. And here I'm asking Formulab to visualize the message passing schedule for this particular variable that I'm requesting, so theta. And what Formulab then does is it takes the edge for theta, it visualizes the two connecting nodes, and then it visualizes all of the connections of those nodes. And this represents the picture that Bert also showed, where a node draws in information from all of its connected edges, summarizes that, produces a message going outward. And in a Forney-style vector graph, every variable on every edge is just connected to two nodes, so you just get the product of two messages. And so this isolates, this zooms into this graph, and it shows what information is being pushed towards this edge. So we can now execute that inference algorithm. In order to do that, I am defining a data structure for the messages. So that is an array of type message. I'm going to initialize a data structure for the marginal distributions on the graph. It's currently an empty dictionary. And I'm going to initialize, or I'm going to make a data structure for the data, the observed variables. That's a dictionary, and I'm going to say that this variable called x1 is observed with value 1. So you got the first question correct. Then we have this step function here. This has been generated by Formulab in this procedure defined above with the message passing algorithm. And what it does, remember that this exclamation mark, it populates certain, or it changes its input arguments. So what happens here is that it populates this marginals dictionary and this message array. So yeah, we execute that, and then we can print out the messages, and it shows that there are actually two messages here. The beta distribution 1,1 and beta distribution 2,1. Alright, so Formulab has spit out two messages, but do these actually make sense? Where do these parameters 1,1 and 2,1 come from? So if you remember Bert's lecture, he talks about the general formula for sum product message passing. That's this mental picture that you should have. You have a factor node f here, which summarizes all of the incoming, which summarizes all but one incoming edge, in this case x1 up to xn, and then pushes out a message towards a specific variable y in this case. So the prior node is not connected to any other unknown variables, so its message for theta is actually just its standard distribution. It's a terminal node, it just, yeah, there's no summing over unknowns, other unknowns. So that is a beta distribution of 1,1, which verifies the first message Formulab built. Similarly, we can derive that second message from the likelihood node by hand. For this, you need to know that if a variable is observed, then we say that it has a distribution based on a delta, a direct delta distribution, where the variable x1 has the value 1. So Bert also talks about this direct delta distribution, so have a look there if you're puzzled by this. So if we apply that general rule for sum product message passing, so we take this message from the observed variable x1, which is that delta spike, and then we take the factor node function, which is Bernoulli, resulting in this functional form. Then because of the sifting property, we get theta to the power 1 times 1 minus theta to the power 1 minus 1. And if you remember that a beta distribution is proportional to theta to the power alpha minus 1 times 1 minus theta to the power beta minus 1, then you can read this last line as a beta distribution with parameters 2,1, which verifies Formulab's output. So if you look at these messages visually, that produces this graph. So this red line is the message from the prior, and I told you before this is an uninformative prior, and this is what uninformative priors look like. all values of theta are given equal probability prior to observing data. So that's just a straight line. This other message is it's a linear increasing line. Note that I've already mentioned this in the first probabilistic programming session, but note that probabilities for continuous distributions for densities can be larger than 1. The point is that the density, the PDF, integrates to 1. So you can see here it's 2 tall and 1 wide, so it produces a square, and then it's a triangle, so you cut it in half. You can see that this integrates to 1. Right, so those two messages, they meet on the factor graph at the edge for theta, and then where they meet, you take that product, and that produces the marginal distribution for theta, which in this case represents the prior for theta, so theta given x1. So if you multiply two beta distributions, you get another beta distribution, and so the new shape parameter alpha is the sum of the old shapes, sum of the old alphas minus 1, and the new beta is the sum of the old betas minus 1. So in our case that would be 1 plus 2 minus 1 is 2, and 1 plus 1 minus 1 is 1. And so if we request from the marginals dictionary the variable theta, it produces a beta with parameters 2, 1, which again matches our manual derivations. So if we plot that, you can see that the marginal, this purple dotted line, lies exactly on top of the second message, which is caused by the fact that the first message is an uninformative prior. It has no effect on the posterior. Right, so now we are moving into a more general situation where we have multiple questions. So you're not judged on one question alone, you're judged on multiple questions. And we'll be looking at the specific case of 2 questions, but this setup will generalize to any number of questions. So we now have x1 and x2. We have 2 likelihoods, p of x1 given theta and p of x2 given theta, and then the prior p of theta. And you'll, if you remember Bert's lecture, you'll see that this theta appears in 3 factors, and so therefore we need an equality node. And if you want to know more about the equality node, have a look at Bert's lecture. He explains in detail how this works. I'm not visualizing theta prime and theta double prime here. I'm just showing you this this specific place for theta. So Fa and Fb are still exactly the same. Fc is also a Bernoulli, but then of the second outcome variable, and it has the same rate parameter theta. If you now encode that into a graph, so we start a new graph. We say that theta follows a beta distribution. We've now used a different prior parameterization, so it's no longer an uninformative prior, but the company assumes that you must have some skill level if you decide to apply for this position, which is encapsulated by these 2 prior parameters. So we have 2 likelihoods here. x1 is Bernoulli distributed, x2 is Bernoulli distributed, and then we get the following graph generated. You can see it matches the graph above. It's again flipped vertically. Fa is the beta prior with 2 clamped parameters. We have a outcome variable x1 and an outcome variable x2. And then we have 2 likelihood nodes that are Bernoulli distributed, Fb and Fc, and they're connected via an equality node here. So if we ask Phonylab for the message passing schedule for the unknown variable theta, produces this graph where the prior sends out this message above, the likelihoods send out a message here, and then at the equality node it gets summarized and pushed down there. And you can actually inspect the source code that is generated by Phonylab. So you just print source code. So it has this step theta function that you already saw, and now you can see that there are 4 message computations, message 1 to 4, and there's 1 marginal for theta. You can see that message 2 comes from Bernoulli node, message 3 comes from Bernoulli node, and that message 4 is dependent on messages 2 and 3, and also that the marginal is the product of messages 1 and messages 4. So if we inspect these messages, and we do that with this, but by executing the inference algorithm, populating the marginals and messages data structures. And I should say here that suppose you got the first question right and the second question wrong, then we get the following messages. So the first one is unsurprising, that's the prior. The second one is also unsurprising, that's the same as before. The third one is its mirror in shape parameters, and which is unsurprising because you got the question wrong, but I do encourage you to do the derivation for this message yourself. It follows the structure of the first message derivation, the one for message 2, exactly, but you have to use x2 minus 0 instead of d1 is x1 minus 1. And then the fourth message, the one from the equality node going downwards, has these two parameters, 2, 2. And so if you look at the manual derivation for that, yeah, we have an equality node specified here with this f equals. And here I have drawn theta prime and theta double prime. But you can see it results in the product of those two likelihood messages. And when you use that rule for updating, for the product of two beta distribution, for updating the shape parameters, you're going to end up with beta of 2, 2, which matches what Formulab already computed here. So if you visualize these messages, yeah, this black line is the same right answer distribution as before. The green line is its mirror because you got the question wrong, and then the product of those two produces this renormalized product of those two produces this fourth message, which is symmetric around this 0.5 value. And then if we visualize the prior, which is this red one, you can see it now favors it. Your company already assumes that your skill level must be somewhere in this range, probably if you intend to apply for this position. And then you got two questions, one right, one wrong, which pushes you towards maybe this guy is or girl guessing at random. The overall picture of that produces a marginal with, you do assume that this person has skill, but it's less than the prior. It's an average of the observations in the prior. Right. That concludes it for the first part. In the second part, we'll be looking at score questions, a different kind of question, and we'll use a different model to tackle that. I encourage you, so the whole point of the probabilistic programming sessions is for you to get your hands dirty, to try out things yourself. So I encourage you to play around with, okay, what if you got both questions right, or what if you got both questions wrong, and see how that how that affects the message computations and the estimate of the marginal. So have fun, and I'll see you in the next part.